Hi there, this is exercise 21B. We're doing this in two parts, and that's partly because I'm going to introduce you to two different ideas. But the coefficient of friction is something which is an important idea. I suppose it relates to the fact that on some surfaces, they're really rough surfaces, and there's lots of friction. On other surfaces, there's hardly any friction at all. And I suppose the coefficient of friction is a way to try to get a mathematical handle on the extent of the friction. So we're going to look at it here, and of course friction is really important because without friction you can't move at all. You just slide, but too much friction you can't move at all either. So it's a weird idea. Well, a little starter for us. Let's have a look at this. A force of 5 newtons acts on a particle. So I'm just going to draw my particle. There he is. It acts on a particle of 5 newtons. I'm going that way. It's a 2 kilogram. If the particle is initially at rest, how many seconds will... Oh, right. So I think this is one of those ones where it says F equals ma. And once I've dealt with the F equals ma part of it, I can then jump over to suvat. And we got these two different sort of systems, but of course the A appears in both. So F equals ma. I know the force is 5. I know the mass is 2. I can work out the A. So 5 divided by the 2 equals A. A equals 2.5. So I now know what A is. What's it tell me? Let's write out suvat. I always write it out like this. And then I kind of work out which ones I need or want to need. After how many seconds? So I want the time. Will the displacement be equal to 5 meters? And of course I now know that A is 2.5. Does it start? It's initially at rest. So S equals, it's crying out for S equals ut plus a half at squared. 5 equals u, which was 0, so 0 times anything, that disappears, plus a half of a, well that's 1.25, times t squared. So presumably 5 divided by the 1.25 equals t squared. I think that equals 4. So therefore t equals plus or minus 2. I don't even get a negative time in this respect, so I'm going to say t equals 2 seconds. 2 seconds, there you go. How strange is friction? It is strange. I do think it's strange. It's one of those things which you can be pushing quite hard on a heavy desk or a big cupboard or something, and it doesn't move at all. And you can push with a force of, I've said here, 10 newtons, and it won't move. But this is the weird thing. The friction sort of matches your push. So if I push with 10 newtons, it doesn't move. So effectively the friction going the other way, these two have to be equal. It can't be more than 10. But weirdly, if I push more, say I push 20, and I'm really pushing now, it's really, really working at it, but the friction says, nope, still not moving. And now the friction must be equal to 20. What's weird is, there comes a point at which the friction can't beat you anymore. You kind of win the fight, and your pushing exceeds the amount that friction can push back. And on that basis, it starts to move. So I've said here, if I push with a bigger force, I say 20, the object won't move. Note, however, the friction is now 20. By pure fluke, I picked the same numbers there. We basically call that in equilibrium. But at some point, let's say 30 newtons, friction is now bigger than, sorry, not able to compete. The force I push with is bigger than, say, the maximum amount of friction, which I'm suggesting is 20. And therefore the object will move. Notice I'm suggesting there's a maximum level of the friction. And this is right. We call it the limiting friction. So when the pushing force is the same as the limiting friction, it's almost ready to move, not quite. So we might, for instance, have, if I just drew a picture up here. Ooh, where's my pen gone? So if I draw a picture up here, I might have this object put on the floor. And it might be the fact that the limiting friction on this, let's write this down, this is the max, the F max we'll describe it as. F max might be equal to, say, 20 newtons. If I push with 20 newtons, it's not going to move. but we describe it's been on the point of slipping. It's just about to move. So when you go above it, say I go 120 newtons or something, it will start moving. It will accelerate. Acceleration, of course, is this idea of the limit being broken. And this is our formula. F max equals mu r. This mu is the weird thing. That is the coefficient of friction I've been hinting at. So F max equals mu r. Write it down. In reality, in most situations, F equals mu r. But if it's in equilibrium, it's not. There is a maximum value, and the friction might not be as much as as it could go up to. F equals mu r. R, by the way, is the normal contact force. It's all to do with the weight of the object. So here's my picture. We've got this particle. It's being pushed to the right, but there's a friction holding it back. And that friction is determined by mu, which we will discuss in a bit, and also the r. And of course, r is linked to the weight. R equals w in this case. Not always equal to w, but in this particular case, forces up equals forces down, r equals w. So in this case, we've got r equals w. We've got F, therefore, equals mu r. And depending on how big the pushing force is, if it's bigger than I can muster with F equals mu r, then it will move. If it's smaller, then it won't. But this tells me the maximum the friction can be. So we often write, therefore, that F is less than mu r, because by definition, the real friction that's acting can't be bigger than mu r, but it might be less, depending on whether or not it stays at rest, or if it starts moving. If it does start moving, then F max is equal to mu r. Or likewise, if it's on the point of slipping, as I explained just now. So basically, we talk about it being less than or equal to mu r. That's a good way of describing it. But think of it as F max. Now, what is the coefficient of friction then? Well, I got this off, I think it was Wikipedia or something like this. And so basically it shows you what the coefficient of friction would be between two materials. So for instance, if I've got, let's pick on one, if I've got some concrete on the floor, and I've got something made out of rubber, it could be a rubber wheel or some base of a cupboard. If you can see it says concrete and rubber, the friction, what they've called the static friction, is equal to 1.0. And obviously if it's wet, it's lower, it's less friction if it's lower. But interestingly also, they're saying if it's moving, kinetic friction is lower as well. It's 0.6 to 0.85. And that might be something you've noticed in the past as well. Once you start moving something, it's actually easy to keep it moving once it starts moving. But once it stops again, you've got more of an effort. Now in maths, we only really consider the static friction, and we don't really care that the kinetic friction is likely to be lower in real life. But notice, for different things, so if I've got something brass, which is a form of copper, and something steel, and they're sort of rubbing against each other, it's much lower. It's 0.35-ish, going up to 0.51 according to this. But you can get some values which are, look at this one, cast iron and copper, which is greater than 1. I used to always think that mu had to be less than 1, and that actually turned out to be wrong. Mu can be bigger than 1 if need be, depends on what they are. But you can see most of these are less than 1, which might have explained my ignorance when I was first thinking about this. So the coefficient of friction is something we're often asked to find. This one says a box is being dragged at constant speed, this is probably the box, in a straight line along a rough horizontal surface. So this is a rough floor. Now when it's rougher floor, of course, you get friction. It's being pulled along this floor by a horizontal cord. Presumably this is the cord, and it's giving it some kind of, I'll call it a tension. The coefficient of friction, it says, between the box and the ground is 0.4. It says it as well, look at this, it's being dragged at constant speed. Now as soon as you say constant speed, that means the tension is equal to the friction going the other way. So that's important. We know the tension equals the friction, but this will also have a weight, this box. What is it? It says it's 200. 200 newtons, and it's not being pulled up at all, so therefore we can quite happily say that R must also equal 200. So it says that this T equals F, but of course we know that F equals mu R. So mu, they tell me that, don't they? They say the coefficient is 0.4. 0.4 times the R value, which I have worked out has got to be 200. So is that 80 newtons? That tells me the tension in the cord is 80 newtons. 80 newtons, there you go. The second example, a box of mass 20 kilograms. So this is now a 20 kilograms. And of course that means I can calculate the weight. Weight equals, well, mg. And mg in this case is 20 times by 9.8. Should know the 9.8, which is 196. 196, so W equals 196. Now it's tempting to think therefore the weight is equal to 196, not the weight, the R value, but it probably isn't, because this, I haven't read it yet. The rope makes an angle of 30. Oh, it's being dragged along this floor, so it must have a tension here, and the tension in the rope is 80 newtons. T equals 80. Now you remember you have to resolve these. If I want to resolve it going forwards, here, that would give it a force of T. So I'm just going to do this. I'm going to resolve it. This is T cos 30, or 80 cos 30 if you prefer. There's also got this force going upwards, which is T sine 30. That's called resolving that force. So let's just go through this. Up and down, I'm just going to say, oh, there's one other force I want to put on, and that's the friction. There we go. Up and down, we've got R definitely going upwards, but also this T sine 30, which is really 80 sine 30. That equals the force going down. There's only one force going down. That's equal to 196. So what's 80 sine 30? Well, I know sine 30 is a half, so that must be 40. Type it into your calculator, just make sure. I might have done it wrong. And therefore R, if I move the 40 over, I get 156. Notice the reaction force is lower than it would otherwise have been. It would have been 196, but because I'm pulling up slightly, R is smaller. It's 156. So now I know that R is 156, I can work out what F is. F, is it moving this thing? Yes, it's got an acceleration. So we're definitely moving it more than it's being stopped by the friction. So F is equal to mu R. I don't have to worry that less than or equal to stuff. And does it tell me what mu is? Oh, find the coefficient of the friction. So I'm not going to work it out. Mu times by whatever R was, which was 156. That's all I can say. F equals that. But what I can say is, I suppose, I can say F equals ma as well. This is the rule for all particles in motion. It's called Newton's second law. And there are two forces acting in the direction of the motion. There's the T cos 30, which is 80 cos 30, which is pulling it, but then it's being slowed down by the F. And I'm going to probably write that as 156 mu. 156 mu. And that equals ma. Well, do I know the mass? Yes, the mass was 20. Do I know the acceleration? Yes, I know it's 0.5. And I think this is enough then to work out what that is. I'll do 80 cos 30. I need to make sure my calculator's in degrees. Good job, I checked it wasn't. 80 times cos 30. That's 69.3. Minus 156 mu. Presumably that equals 10. So switch those around. I'm going to do it up here because I'm running out of space. 156 mu equals 59.3. So if I do that divided by 156, I get mu equal to 0.380. I don't know if that's right or not. Let's have a look. 0.380 to 36 figs. Now I'm almost out of time, so that's all I can do in this video. But I want you to go through what we've gone through. There's a couple more examples. Well, there's actually quite a lot of examples we're going to do. And then in class we will do exercise 21B. But there's certainly a lot for me to talk about in lesson before we even get started on exercise 21B. And remember, this is the first part. There's also a 21B.2 coming your way. So all the best, and thank you very much.